The future of AI is not just limited by chips, it is limited by something much more fundamental: power and heat. Today, some of the most advanced AI systems in the world require as much electricity as a small city, and keeping them running has become one of the biggest challenges in modern history. As AI models grow larger and more powerful, the amount of energy required to run them is increasing rapidly. Training a single large model can consume enormous amounts of electricity. But energy is only part of the problem, because almost all of that energy turns into heat. And if that heat is not removed, the system cannot function. Chips slow down, performance drops, and in some cases, hardware fails. For decades, data centers relied on air cooling: fans, airflow, and large cooling systems. But modern AI hardware is too dense. There are too many racks of compute, too much power, in too small a space. No amount of airflow will suffice. To solve this problem, the industry rapidly moved towards liquid cooling. Instead of using air, liquid is used to absorb and carry away heat directly from the chips. This allows systems to run at much higher power levels while maintaining stability. There are multiple types of approaches here. Direct-to-chip cooling, where liquid flows through cold plates attached to processors. And we also have immersion cooling, where entire systems are submerged in special fluids. All designed to solve the same problem: removing heat as efficiently as possible. But one of the most surprising developments is the temperature of the cooling systems themselves. Some of the latest AI platforms, such as the NVIDIA Vera Rubin, are designed to be cooled using water at temperatures around 45 degrees Celsius. That is not cold water, it is basically warm water. And yet, it is used to cool some of the most powerful chips ever built. Because at this scale, efficiency matters more than temperature, and warmer cooling systems reduce energy waste and improve overall performance. This changes how data centers are designed. Cooling systems become part of the infrastructure. Energy efficiency becomes critical, and in some cases, the heat generated by AI systems can even be reused to heat buildings or entire facilities. This means that the future of AI is no longer limited by software or even hardware alone. It is limited by energy, by how much power we can generate and how much heat we can remove. This shift is changing how AI infrastructure is being measured. As NVIDIA CEO Jensen Huang said, future AI data centers will be measured not in chips, but in power, in gigawatts. If you have access to a fixed amount of power, for example 2 gigawatts, then that becomes your hard limit. You can only deploy as much compute as that power budget allows. Which means that the goal is no longer just building faster systems, but extracting the maximum amount of computation from every single watt. In modern AI, efficiency is therefore no longer optional, it is in fact the constraint. And as these systems continue to scale, another challenge emerges: connecting them together at massive scale. In the next episode, we will review the networks behind AI.